So in 5.2, we're going to look at a process known as strong induction. And our second axiom, strong mathematical induction, or 2PMI for the second principle of mathematical induction, says that to prove that the predicate P of n is true for all n in A, where A is a subset of the natural numbers, just like we had before, typically we'll start either at 0 or 1 and proceed from there. In our first example, we'll actually look at the case where A consists of the integers greater than or equal to 50, but it should be fairly clear from the context what your starting A value is. And generally, in the problems that you would see in this class, we're going to have some starting little n value, and then we'll look at all the integers greater than or equal to that. We're not going to be skipping integers after the starting one. But the process is similar. We're going to have a basis step or basis steps, and that's also the case with regular induction. In the examples that we've seen so far, we don't need multiple basis steps or basis cases, but you may run into a situation where that's necessary, and that's more likely to happen with strong induction, but that's not the distinguishing feature of strong induction. The distinguishing feature is that in our inductive step, to show that for all k greater than or equal, or we're going to show that for all k greater than or equal to n sub 0, if p of n sub 0, p of n sub 0 plus 1, n sub 0 plus 2, up through p of k are all true, then p of k plus 1 is also true. Or you can assume up through k minus 1 and then show p of k. But we're assuming not just the truth of p of k, but we're assuming that p is true for all values up to and including k. So not just assuming that it's true for k, but for all the values up to and including it. So we have a much stronger assumption that we're putting on this. We're assuming that all of these things are true, and then showing that all of them together imply the truth of k plus 1. So if we think of the climbing a ladder example, instead of assuming that you can get from the kth step to the k plus first step, or assuming that you can get to the kth step, showing that you can then get to the k plus first step, here we're assuming that you can get on any rung of the ladder from between the, say, the first one up to the kth one, then we can get to the k plus first. So maybe there's a trampoline on the k minus first rung of the ladder, or something like that. Something farther down on the ladder that's going to help you get to the k plus first rung of the ladder. So you don't need just the things that you've brought with you to the kth rung, but if there's anything on the k on the lower rungs of the ladder, you can use those to help you get up to the k plus first rung of the ladder. So the template for strong induction, we're going to have our basis step or steps, or our base case or cases, however you want to label that. We're going to show that p of n sub 0 and n sub 0 plus 1 and so on out to p of n sub 0 plus j are all true where n sub 0 is the smallest n value, and j is the number of base cases needed to, this should just say base cases or basis steps, needed so that we never use anything before p of n sub 0 in the induction step. Again, this is not the distinguishing characteristic of strong induction. However, it's more likely that when you're using strong induction, you may run into a situation where you need multiple base cases. Then in your induction hypothesis, and this is the primary difference, you're assuming that you have a k value greater than or equal to n sub 0 plus however many base cases you need to shift things down by. But you're assuming that p of n sub 0 and p of n sub 0 plus 1 and all of these up to p of k are all true. So you're not just assuming that p of k is true. Rather, you're assuming up to and including p of k are all true. And now in our implication, again, we're assuming this conjunction. We're assuming that we have all of these predicates satisfied, that these are all true, and showing that that leads to the truth of the k plus first case. So we're proving this implication. And then we'll conclude by strong induction that P of n is true for all integers greater than or equal to n sub 0. So let's look at an example. I'm going to prove that any amount of postage totaling 50 cents or more can be composed of 6-cent and 11-cent stamps. And we wouldn't have to do this with stamps, but it's maybe more likely that you'd have stamps in these unusual denominations than you would have with, say, coins. What we're going to look at, so we'll still have our base case. And we need at least the 50 cents of postage situation. So for 50 cents of postage, we can use 4 11-cent stamps and 1 6-cent stamp. So 50 cents worth of postage can be written as 4 times 11 cents plus 1 times 6 cents. Now, in this example, it turns out we are going to need multiple base cases. It's not immediately obvious, though, that that is the case. Unless you've done a problem like this before, then you might have some idea of how many you need to show. But we'll see later on that, or how we can figure out how many base cases we actually need. So leave some space here, but let's move on to our induction hypothesis. And we're going to assume that, and in this case, we're going to state it, we'll have another variable j and the variable k. Assume that j, any amount of postage, any amount postage, j cents, where, and then in your induction hypothesis, you need to state the range, basically, where j is greater than or equal to 50, less than or equal to k. Oops, k. So we're assuming a range of values, assuming that's true for up to and including k. So that's why I need this other variable. I can't just use k. So where j is greater than or equal to 50, less than or equal to k, and k is greater than or equal to the smallest one, so it's possible that this range includes just the 50th case. So assuming that any amount of postage, j cents, can be composed using 6-cent and 11-cent stamps. So if this were a regular induction problem, I would just say assume that for some amount of postage, k cents, where k is greater than or equal to 50, we can compose that using 6-cent and 11-cent stamps. So now let's look at our induction step. And just like with regular induction, we're going to look at the k plus first case. And so we want to show how we can use our induction hypothesis to compose this using 6-cent and 11-cent stamps. Well, my induction hypothesis applies to any amount of postage up to, and how we've stated it so far, up to k cents, from 50 cents up to k cents. And so we need to somehow write k plus 1 in terms of a lesser amount of postage. So we can take our k plus 1 cents and write it in the following way. K plus 1 is going to be equal to, Well, I have 6-cent and 11-cent stamps, and in general, when you're doing these sorts of problems, you want to basically pull off the smaller denomination of postage or bills or whatever you're looking at. So I'm going to write this as 6 cents plus, and then to get to k plus 1, I would have k minus 5. So now we can get the 6 cents of postage from one 6-cent stamp. And then by our induction hypothesis, since k minus 5 is less than k, we can just say less than or equal to, that's the range of j values that we're assuming it for. We could say strictly less than k, but it's also true that's less than or equal to. And because that's greater than 50, now this isn't quite right, we'll need to fix that in just a minute. So since k minus 5, we would need it to fall in this range, greater than or equal to 50, less than or equal to k. So as long as k minus 5 falls in that range, we can compose k minus 5 cents of postage using 6-cent and 11-cent stamps. And thus, and we'll go back and fix some of the issues in just a minute, but that, as long as everything there is correct, and it's not quite correct yet, but thus k plus 1 cents of postage can be composed using 6-cent and 11-cent stamps. And then our conclusion reads very much the same as our previous examples. We would just say, therefore, thus, whatever word you want to use, therefore, by, you can say either 2 PMI or by strong induction. Sometimes you'll just see induction mentioned because they are equivalent, as we'll get into a little bit more in just a minute. But we'll go ahead and emphasize which form of induction we're using. So thus by strong induction, the result holds for any amount of postage 50 cents or greater. And that would complete the proof. Now, I mentioned that there was a problem back here. What's the problem? Well, our induction hypothesis applies to J, some amount of postage, greater than or equal to 50 cents, less than or equal to k cents, where k is greater than or equal to 50. So when I'm looking at this range down here in the induction step, we split off basically in our k plus 1, we took away 6 cents because we know that we can get that from a 6-cent stamp. And then we need to justify why we can write the k minus 5 cents worth of postage as some composition of 6-cent and 11-cent stamps. So if we're going to use our induction hypothesis, we have to make sure that k minus 5 falls in the range of values covered by that induction hypothesis. So I need k minus 5. Well, I need it to be less than or equal to k. That's fine. It depends on k, so we know that k minus 5 is going to be less than or equal to k. But the greater than or equal to 50, well, that's not necessarily true because we just said that k has to be greater than or equal to 50 up here. That's not actually going to be the case if I have k equal to, say, 50, 51, 52, 53, or 54. So in order for this part of the inequality to be true, I actually need to assume that any amount of postage j cents where j is less than or equal to 50, greater than or equal to greater than or equal to 50, less than or equal to k, and k is greater than or equal to, I need to make this 55 here in order for this inequality to always stay in the appropriate range. So in order for k minus 5 to always fall between 50 and k, I need to make sure that k is at least 55. And so that means that back here in our base case, our induction hypothesis is going to kick in basically when we're looking at our induction step, I guess, will cover amounts of postage that are 56 cents. If my smallest k value is 55, then the induction step starts when we're looking at 56 cents worth of postage. So our induction step will cover 56 cents worth of postage and above. Our base case only covered 50 cents worth of postage, at least so far. So we have the amounts of postage, 51 cents through 55 cents, that we haven't justified. We haven't explained why those can be written as a combination of 6 cent and 11 cent stamps. So because I had to adjust this k value, if this couldn't be less than 50, if the k minus 5 I knew was going to stay greater than or equal to 50, then I wouldn't need any other base cases. But because it depends on k, because this value here is dependent upon k, then we need to make sure that k stays large enough so that the k minus 5 stays bigger than the smallest value we're trying to prove this for. And that means that I need to come back here and add in some more base cases. So I also need to show that 51 cents worth of postage, 52 cents worth of postage, 53, 54, and 55 cents worth of postage can all be written as a combination of 6 cent and 11 cent stamps. And then the induction process is going to kick in and take care of any amount of postage 56 cents or greater. So all we need to do is just write out the combinations that are going to give us the amounts of postage that we see here. So for 51 cents, I can get that by, and we'll actually use this when we go through and talk about how you could do this problem with regular induction. To get 1 more cent of postage, as long as I have an 11-cent stamp, I can just take that one 11-cent stamp and replace it with 2 6-cent stamps. And I'll go from 11 cents to 12 cents. With that particular combination of stamps. So here, if I take away one 11-cent stamp and have 3 11-cent stamps and add in 2 more 6-cent stamps, that'll give me 51 cents. Take away another 11-cent stamp, add in 2 more 6-cent stamps, that'll get us to 52. Take away one of those 11-cent stamps and add in 2 more 6-cent stamps. That'll give us to 53. Take away the last 11-cent stamps, so 0 11-cent stamps, and just use all 6-cent stamps. We need 9 of them in that case. And then for 55 cents of stamps, we're back to a multiple of 11, so I can then use 5 11-cent stamps, and I don't need any 6-cent stamps for that combination. So we've shown that any amount of postage, 50 cents through 55 cents, we can write it as a combination of 6 cent and 11-cent stamps. And then for anything greater than 55 cents, we can apply our induction process that we see here. Now, let me go ahead, I've mentioned this a couple times, but let's go ahead and jump down to the end of the section. We've got a few more examples here that we'll go through. There's another principle known as the well-ordering principle, WOP. Every non-empty subset of the natural numbers has a least element, has a smallest element in it. That seems fairly intuitive. The theorem for here, though, is the important one. The well-ordering principle is equivalent to both the principle of mathematical induction and 2PMI, the second principle of mathematical induction. And what this is saying is that all three of these, well-ordering, principle of mathematical induction, and the second principle of mathematical induction, these are all equivalent to each other. Now, we're not going to get into into the well ordering principle this semester. I have an example here, but there's not usually time to cover it. And the main focus are the different forms of induction and understanding that process. But what this theorem is saying is that any problem that you could do with regular induction, you could also do using strong induction, and going in that direction wouldn't require too much of a restatement. You would just assume more, but you wouldn't actually end up using them, so it would be kind of silly to do that. Or you could restate the problem so that you're looking at some sort of subset concept. So you are focusing on different subsets of the natural numbers. Your kth case is a different subset. And using the fact that every non-empty subset has a least element, then you would prove your statement. Rephrasing a problem that you would normally do with PMI or 2PMI in such a way that you can use the well-ordering principle is going to be fairly tricky, but sometimes there are situations where you're dealing with subsets more, and it would make more sense to do an inductive proof, inductive style proof using the well-ordering principle instead of the other induction methods that we've seen. The more important one for us is that mathematical induction and the second principle of mathematical induction, even though it seems like you're assuming more in 2PMI, this means that there's actually going to be a way, and it may not always be easy or obvious, but there will be a way to restate the problem or to work through the problem in such a way that you can use, if you're doing 2PMI, you can rephrase it so you can use just PMI instead. That's usually going to be fairly difficult. A lot of the examples that we'll see will need to use strong induction, or that'll be the easier way, just in the way that things are stated, the way that it's phrased. So here, for instance, in this example, it's going to be more natural in this induction step. It's a lot easier to just say, let's pull off 6 cents worth of postage, and then justify why the k minus 5. I need strong induction here because I'm not relying on the kth case, I'm relying on the k minus 5th. So I need to assume back to the k minus 5, or I need this range of assumptions because I'm not, in my induction step, just using the k, I'm using k minus 5, something less than k. We could rephrase that example with the postage in such a way that we can use regular induction, though. I'm not going to go through the entire proof completely formally, but let me sort of sketch through what you would do for your induction hypothesis. Suppose that k cents worth of postage can be composed with 6 cent and 11 cent stamps. And then in your induction step, show that k plus 1 cents worth of postage can be composed with 6 cent and 11 cent stamps. So if I'm going to write this up with regular induction, we need to show that we can always, when we're given k cents worth of postage, that we can always get 1 more cent worth of postage. And to do that, well, we kind of went through this part of the reason back up here. We were writing out our basis case, our base cases. So here I do need base cases. But when we were looking at the going from 50 cents to 51 cents, we noted that if I take one 11-cent stamp and replace that with 2 6-cent stamps, then I get 1 more cent of postage in the composition. So if we have at least one 11-cent stamp, then replace one of them with 2 6-cent stamps. A 1 11-cent stamp in the k-cent composition, replace with 2 6-cent stamps. If not, then I can't just say take one 6-cent stamp and do something with it. If you go through, and this would be part of the scratch work that you would need to determine how many base cases you're going to have, I would need at least, if we look at multiples of 6, well, if we take 3 times 6 cents, that's going to give me 18 cents. That's more than 1 away from a multiple of 11. And if I take 4 times 6 cents, that's 24 cents. That's 2 away from a multiple of 11. Basically, I'm looking for a multiple of 6 cents that's going to be 1 more than a multiple of an 11-cent stamp. Actually, I'm doing this in the wrong way. I want a multiple of 6 cents that's basically 1 less than some number of 11-cent stamps. So 5 6-cent stamps, that's 30 cents. Well, that's 3 less than 33, so that's not what I want. 6 6-cent stamps gives me 36. Next highest multiple of 11 is 44, so I don't want that. 6 times, or 6 cents, 7 of those would give us 42 cents. That's going to be 2 less than a multiple of 11, so that's also not what I want. 8 times 6 cents is going to give us 48. That's also not what we want. But then if we go to 9 times 6 cents, that gives us 56 cents worth of postage. And so if I have an 11-cent stamp, I just need one 11-cent stamp. We can replace that with, or sorry, that should be 54, not 56. That's what we want. So 9 6-cent stamps give us 54 cents worth of postage. So one 11-cent stamp, I can replace that with 2 6-cent stamps and increase the amount of postage by 1 cent. If I have 9 6-cent stamps, then we can replace those with 5 11-cent stamps to increase the amount of postage by 1 cent. So if we have
at least 9 6-cent stamps in the K-cent composition, then we're going to replace them with 5 11-cent stamps.
And so through your base cases, that's where we would go through and justify. So here I still need multiple base cases, and we would still need to show that with our K-cents of postage, we would need that to be greater than or equal to, let's say 54, if we're looking back at our previous base cases, we could work that out. So showing that we have from 50 cents, we have at least one 11-cent stamp. So from 50 cents through 54 cents, we fall into either of those two cases that we've mentioned. We either have at least one 11-cent stamp, or we have at least 9 6-cent stamps in that composition. And if I replace 9 of these 6-cent stamps with an 5 11-cent stamps, then I can work through those 5 6-cent or 5 11-cent stamps and keep replacing them with 2 6-cent stamps. And you would want to maybe add also some justification so that as you looking at these base cases, now we start over again with 5 11-cent stamps. So maybe go ahead and you can include the 55 if you wanted to. Mention that once we get up to 5 11-cent stamps, those are going to get replaced with 10 6-cent stamps if you're going on to the next multiple. Or rather, once you get to the 9 6-cent stamps, then you end up with those 5. So as you start replacing them, you end up with the numbers that we see here. So we would have we'd have that, we'd have the 1 11-cent replaced with the 2 6-cent, and we build that back up. And by the time we've used up all those 5, we have at least 9 6-cent stamps then in the number of 6-cent stamps that we're looking at. And then we replace those and continue on. So you're either going to have 2, 4, 6, 8, 10 6-cent stamps in the composition, and then you replace 9 of those with 11-cent stamps, or you'll have 1 3, 5, 7, 9 6-cent stamps before you reset and replace with 11. So depending on what multiple you're looking at. So the regular induction way is actually going to be a little bit messier if you add in all those details. It's a little bit trickier to show that you can go from, because here we have to start with k cents and then go to k plus 1. Whereas with strong induction, we can use that k minus 5 and show that we can replace that. So we just need that additional induction hypothesis. We have this restriction on our k values that we realized we needed later on. And then we had to add in a few more base cases. But other than that, writing up the induction step and making sure that we've covered all of our details that we need to there is going to be easier than if you're trying to go through with regular induction. There's more subtleties going on there. So with those composition type problems, strong induction is usually the better way to go. So now let's look at another example that uses strong induction. Prove that any integer greater than 1 is either prime or the product of 2 or more primes. And this is sort of proving the fundamental theorem of arithmetic. We're not proving the uniqueness part of the composition or the decomposition into a product of primes, but we're proving that we can look at a prime factorization of some sort. So we're going to start with our base case. And here we're going to consider, well, we're proving this for any integer greater than 1. So our base case should be the first integer greater than 1, i.e. 2. So consider 2. 2 is prime. So it is either prime or the product of 2 or more primes. I have this disjunctive statement, so it's going to be true as long as at least one of those is true. And if you weren't convinced of that, you could add on some more base cases. We don't need these, but 3 is also prime. 4 is a product of 2 primes. Those 2 primes being 2 and 2. Didn't say that they had to be unique primes there. But in this example, we actually don't need multiple base cases. And so there are definitely times when you're doing strong induction where you don't need the multiple base cases, even though it's more common to run into that situation here. So then for our induction hypothesis, now when we're stating our induction hypothesis, we need to be sure that we're stating it, if we're doing strong induction, that we state it correctly for a strong induction. So we're going to suppose that any integer j and then we need to state the range that we're looking at. So where j is greater than 1, say strictly greater than 1, you could say greater than or equal to 2 also, and less than or equal to k for some k greater than or equal to 2. So I'm not assuming that any integer can be written as a product of 2 or more primes. I'm assuming that any integer in this range that we've specified. So for some arbitrary, you could say k greater than or equal to 2. And if you want to say for some integer, just to emphasize that it is an integer, so I'll go ahead and add the arbitrary. Integer k greater than or equal to 2. But we're looking at this specific case. So any integer j in this range, but just for some integer k. So we're not assuming this is true for all integers k, but we're assuming it's true for all j's up to and including the k value under consideration currently. So we're assuming that we can get to the kth step, and we can use facts from the previous steps on the ladder to get to our k plus first. But we're assuming this, any integer j, where j is in that range for that particular k, that these are either prime, any integer j is either prime, or is the product of 2 or more primes. So, and I've got the wrong color there. Oh well. Now let's look at our inductive step, which will mean that we're going to consider k plus 1. So we're going from k to k plus 1. Well, for any integer, there are two possibilities. It's either prime or it's not prime, i.e. it's composite. So if k plus 1 is prime, we're just going to look at those two cases. If k plus 1 is prime, then we're done. You either just say that, or if you want to sound a little bit more formal, then there is nothing more to show. It's a prime, so that falls into one of the cases of what we're looking for in our conclusion. If k plus 1 is not prime, then it is composite. That's just the definition. Composite are all of the non-primes. So k plus 1 is going to be equal to a times b. It's just the definition of composite. For some integers, a and b, where a and b are both greater than 1, strictly greater than 1. It's not prime, so I don't have to have 1 as one of the factors. I could write k plus 1 as 1 times k plus 1, but being composite means that there's some other way to write it as a non-1 integer times another non-1 integer. And these are going to have to be strictly less than k plus 1. If I'm not allowing one of them to be 1, then the other one can't be k plus 1, i.e. a and b fall in the range that we've stated in our induction hypothesis. So, by our induction hypothesis, a and b are each either prime or the product of two or more primes, and thus k plus 1, even if a and b are both primes, that means that k plus 1 is the product of two primes, and if either a or b is the product of more than, or if a or b is not prime and they have more primes in their decompositions, then k plus 1 would be the product of more than two primes. Either one is fine. So thus k plus 1 equals a times b is a product of two or more primes. And then we'll have our conclusion. When you're writing out these induction proofs, go ahead and just explicitly list where you're starting your induction hypothesis, step, and conclusion in your base case. The way I'm writing this out, I wouldn't really need those. I just start a new paragraph, at least with each of these divisions here. I might have a couple of paragraphs in the induction step. In this one, maybe I should have had a new paragraph, at least for the k plus 1 not prime case, just to emphasize that a little bit more. Anyway, thus, for our conclusion, either you can say by strong induction or by 2 PMI, second principle of mathematical induction. And we could rewrite the whole thing in an integer greater than 1 as either prime or the product of two more primes, or we could just say, thus, this result holds. Just to not have to write all that down again. Holds for any integer greater than 1. And that completes the proof. Now notice here that we don't need multiple base cases. The 2 was enough. And the reason that we don't need multiple base cases here is in the part of the induction step where we're decomposing k plus 1 into a times b. The a and the b don't depend on the k for their values. We know that they're going to fall in this range, and so they're always going to be in the range specified by our induction hypothesis, even if k is only equal to 2. If we're just looking at 2, or if we're looking at, I guess we'd be looking at 3 starting there. But we're not saying that a is always going to be some fixed amount less than k, or b is going to be some fixed amount less than k. And so we're not going to run into the same situation that we had in the previous example, where we knew that we could sometimes sort of overshoot that lower bound on the j range that we had. Here, a and b are going to stay in this range, irrespective of what k value we're looking at. So we know that they have to be in here, which means that I don't need multiple base cases. Just the first base case is enough. And then we've got our strong induction hypothesis, and we can go ahead with the proof. All right, let's look at another example, another one where we don't have something maybe quite as mathematical that we're proving, or at least we don't have a formula stated as explicitly. Assume that we have a chocolate bar, and if I end up doing this one in class, and maybe if you're having to watch this while I'm away from class, we'll go through and I'll show you the actual chocolate bar in class. But we have n squares arranged in a rectangular pattern. Now, this rectangular pattern, so we could have, well, you'd normally see a chocolate bar. Maybe you've got something like a, let's say like a 3x4 grid of squares, something like that. We're also going to, the proof that we're going to write up would apply if you had a chocolate bar that was arranged just like that, where you have the squares, the rectangles, in a row. So whatever sort of rectangular grid of chocolate you have will work. And we're saying that the bar, or a smaller rectangular piece of the bar, can be broken along a vertical or horizontal line separating the squares. So if you have like a Hershey's bar, or usually in class I use a Trader Joe's dark chocolate bar, but they'll have those pre-formed from the molding process. You'll have those rectangles, and you can most easily break it along the lower parts of the bar that they have pre-marked out for you in the mold. And so we can break it along a vertical or horizontal line separating the squares. So if I have the squares just next to each other, I'm only going to separate along those vertical lines. If we have a more standard rectangular grid of chocolate, then we'll have both the vertical and horizontal lines. So we're not going to make any breaks diagonally. We're going to assume that it breaks cleanly across those lines, and we're not trying to break it in any other way. And only one break will be made at a time, and each break separates that rectangular bar into two smaller rectangular bars. And we want to prove that's going to take n-1 breaks to break that bar into n separate squares. So I'm just going to break along all of the lines until I get down to n separate squares. And we claim that no matter how you decide to do it, we're going to need n-1 breaks. So if you kind of look through, in this long example, doesn't really matter, but let's say I break here, so that's one break. And then I'd have these two bars, and then I break this again, so that's 2, 3, 4, 5 breaks, and I had 6 squares to start with. Over here we have 12 squares, and so we claim that's going to take 11 breaks. So let's say I start here, well, that's one break, and then maybe I take this long one, 2, 3, 4 breaks, and then this 2x4 square that I have left, maybe I break here, so we're up to 5, 6, 7, 8, 9, 10, 11 breaks. Once I have it broken into these smaller pieces, so if I'm making this break here first, I can't count this vertical as just one break. That's going to take at least 2 from the 2 different pieces, or depending on how I break the 2x4 one, maybe multiple breaks along that line. So if you count up the breaks, irrespective of how you decide to break your bar, there may be a lot of options. If you have just a long bar, there aren't quite as many, but irrespective of how you perform those breaks, it's always going to take you n-1 breaks to get that bar into n separate squares. So let's go through, and we're going to prove this by induction, and we'll use strong induction. So what's the smallest size chocolate bar that we can have? Well, we could have a bar that's just one solid square without any divisions in it. So for our base case, we can say to first consider a bar with one square. Well, it's already broken up into one separate squares. So it's going to take 0 breaks. And we want to show that this follows the formula. That's 1 minus 1 breaks to break that bar into one separate square. Now in this particular example, we're not going to need any additional base cases, but if you weren't convinced or if this was unsatisfying because maybe you think, well, I want a situation where I have to actually break the bar, well then you could also look at a base case where you have 2 bars, and that's going to be easy enough. You don't have to look at multiple ways of arranging those bars. Once you get into, I guess, more than 3 squares in your rectangular pattern, then you have to think about how they're laid out and go through and talk about the breaks that way. But with just 2, there's only one way that you can lay those out in a rectangular grid. And so there you're actually performing a break. And so if you wanted maybe a more, what feels like maybe a more satisfying base case, then you can also state for n equals 2. You do want to start this at 1 because it is possible to have a chocolate bar with just 1 square in it. But for a bar consisting of 2 squares, it takes 1, which is equal to 2 minus 1. So it does satisfy the formula. Breaks to separate the bar, to break the bar into 2 squares. So now let's state our induction hypothesis. And I'm going to first maybe state it the incorrect way. So if we were doing regular induction, assume that a bar, this is the way we'd state it for regular induction, the bar with k greater than or equal to 1 squares can be separated into k separate squares with k minus 1 breaks. And the problem with this, if we look back at our example, either of these, well, I'm not forced into breaking off just a single square at a time. And in fact, it may not be possible to break off just a single square at some point in the process. So for instance, if I end up with a grid 3x4, such as the one that we had here, it's not possible to break off just a single square. And so I can't get to that from the k plus 1 case. I can't actually get to the k case, and so I can't use that in my induction step. If it's not possible to look at the kth case from any possible k plus 1, then you need strong induction. And again, there's a way, and I'm not going to go into it here, but we could figure out a way to rephrase this so that we're doing regular induction in such a way that we can use the kth case to get to the k plus first. But with this particular problem, the most natural way of the way that's been described, and the most natural way to go through and prove it, the easiest way to go through and prove it will be with strong induction. So if I have a row of squares, then I could force that sort of breaking pattern onto it, but we haven't guaranteed that they're all going to be in a row like that. And so we need, instead of induction hypothesis stated that way, as we go through our breaks, we could end up with various sizes of bars. We're never going to have a bar that's less than 1 square. And when we make a break, we're always going to have bars less than the size that we started with. So the way that we're going to state our induction hypothesis, assume that any bar of size j, and we're saying the any with the j because we want to emphasize that we're taking advantage of that entire range of values, where j is greater than or equal to 1. Our base case was for 1, so we can start j there. Less than or equal to k for some k greater than or equal to 1. So whatever k value, whatever kth step we're saying we're at, we're going to show we can get to the k plus first. But assume that any bar of size j falling in that range can be broken into j separate squares in j minus 1 successive breaks. And now, when we look at our induction step, we're going to start with a bar of size k plus 1. And let's say it this way, we have a bar with k plus 1 squares. The assumption here being that they're in a rectangular grid. We won't keep writing that down just for the sake of brevity. After one break, so how are we going to use this induction hypothesis? Well, we're going to perform one break and then look at what we have. Well, once we do that, we have 2 smaller bars. And we'll call their sizes R and S. And then we know something about their sizes. We know that they're going to have to be at least 1 square in size. So both R and S are going to be going to satisfy that part of this inequality. And we're breaking off at least 1 piece of chocolate, at least 1 square of chocolate. So we can't have any more than k squares left in the other one. So they're going to fall somewhere in that range. We're performing a break. If we have just a row of squares, then maybe it's possible to break 1 square off and have k squares left in the other piece. Maybe we have a situation like the 3x4 grid where it's not possible to do that, but when we split it, we are going to be less than or equal to k. So if I have 12 squares, I make a break, I can't have any more than 11 squares left in the largest piece. And then we also know that with these 2 smaller bars, if I add up the number of squares in both of them, that's going to be equal to k plus 1. I started with k plus 1 squares and I just broke them into these 2 separate pieces. But we know that R and S relate to k in that way. R plus S will be equal to k plus 1 because of where they came from. So in this case, the R and the S do depend on k, but we're never going to be in a situation where one of them could be less than the smallest size. And so that's why we don't need multiple base cases. I can't break off a square of size -2 or -3 or something like that. That just doesn't make sense in the context of this problem. And we're assuming that we're actually making a break along a particular line. If I start with 1 as my base case, then k plus 1 is going to be at least 2, so there will be a break that can be made. And now, since these fall in the range specified in our induction hypothesis, we can say that by our induction hypothesis, we can look at the number of breaks that will be needed to finish separating these smaller bars into their individual squares. So it takes r minus 1 breaks to separate the bar of size r into r separate squares. And similarly, it's going to take s minus 1 breaks to separate the bar of size s into its s separate squares. And now we're going to add up all of the breaks that we've performed. So this gives a total of, well, we had the original 1 break plus another r minus 1 breaks for the bar of size r then, plus another s minus 1 breaks for the bar of size s. Really, I should probably also have stated that we can assume that the derivative of a linear function is just the slope. And in that case, I wouldn't need that the derivative constant is 0 because we can just view that as a linear function with slope 0. And then for our n equals 1 case, then we would have x to the first equals 1 times x to the first plus 0 is a linear function. So the derivative is 0, or so the derivative is 1. So stating that we can say something about the derivative of a linear function is really what we need in our for our assumptions if we're going to go through this with induction. You could prove that using the limit definition of the derivative and then show this particular case of the power rule. The power rule applies even when you don't have an integer exponent and also when you have negative exponents, and so the induction would not work in those cases. So now I could justify that why the derivative of x to the first is equal to 1. So really that's the part of the base, or that's the base case of the two here that we're showing. And then the n equals 0, again, that's being proved basically separate from the rest of the induction. So I'm essentially modifying this to start that at 1 and say we're going to look at powers greater than or equal to 1 for our k. So then k plus 1, write it out like that. And then we can finish the simplifying. So this is going to be equal to k times x to the k plus another x to the k, putting those powers of x together, k minus 1, x to the k minus 1 times x to the first. And then we have k plus 1 times x to the k when we factor out the x to the k. And that's what we were trying to show. So our conclusion, just restating it thus, the derivative with respect to x of x to the k is equal to k times x to the k minus 1. And as I've said, I'm going to go back to stating that in terms of n. Typically in our conclusion, So n times x to the n minus 1 for any integer n greater than or equal to 0. And we could just say for any n in the natural numbers if we wanted to make that a little bit more compact. And that would wrap up the proof there. So that's everything that we're going to be looking at in Chapter 5. Got induction, strong induction. We've already talked about the well-ordering principle. The main thing that we're using there is this theorem 4. That is equivalent to both PMI and 2PMI, so any induction proof can be solved using strong induction. Just assume a little bit more. Any strong induction proof can be solved using regular induction, but that may be a difficult direction to go in. Over here, if I wanted to use strong induction, then I would simply break this up. I guess I didn't mention that. I would break this up instead of writing it that way. I would say that we would have the derivative with respect to x of x to the s times x to the r, where s and r are greater than or equal to 1, less than or equal to k, and s plus r is equal to k plus 1. And then we would use the product rule again and do the algebra at the end. And just like in the last proof with the chocolate bar, at some point in the final steps of the algebra, you'd have an s plus r that gets replaced with k plus 1. And that would finish off the proof more generally with strong induction. But here I can always guarantee that I can pull off just a single x, and so I don't really need strong induction. We could just say, suppose that the derivative of x to the k is equal to k times x to the k minus 1 for some k greater than or equal to 1, and not have to state it in the strong induction form there.